see, folks. So here we are. There we are. We've got the chime. Okay, you guys. So we're going to continue talking about limits here. There are some forms that I believe you should just have memorized. As x gets very close to 0, x and the tangent of x basically approach 0 at the same rate as you get very close to 0. And so this is just equal to 1. If you had the reciprocal of this, the limit as x approaches 0 of the tangent of x over x, same exact issue. Those both approach 0 at the same rate when they have extremely small values of x. And so that also equals 1. Same thing is true for the sine of x over x. That equals 1. And the limit as x approaches 0 of x over sine of x is equal to 1 also. So I would just have those memorized, okay? And where things get interesting is you're going to see problems like this, where you have the limit as x approaches 0 of 2x over the tangent of x. You'll see things like this. And how do you handle that? Well, one way to handle it is you can take constants inside and out of these limits at will. It doesn't affect the answer at all. So I could pull that 2 out front, and then that would be 2 times the limit as x approaches 0 of x over the tangent of x. And we've already established that that is just 2 times 1, or just 2. Okay. You could run into another issue. What if they have something like this? The limit as x approaches 0 of x over sine of 2x. Okay. Well, they both approach 0, but the problem is this one doesn't approach 0 at the same rate as that one for very small values of x. And so how do you handle this issue? Well, you kind of do this process in reverse. Remember, you can always multiply a number by 1. And so I'm going to cleverly multiply this by the fraction 2 over 2. And as I said earlier, you can always take a constant and move it into inside and outside of this fraction in here inside the limit at will. And so what I'm going to do is I'm going to move this the one in the numerator, that 2 in the numerator, inside, and I guess I'll leave this as a 1/2 on the outside, okay? So I'm going to rewrite this as 1/2 times the limit as x approaches 0 of, I'm going to put that 2 in there, 2x over the sine of 2x. And so now you'll notice these both agree. The only issue I have here is that I'm saying x approaches 0 and not 2x approaches 0. So you'll notice if you have x approaches 0, if you multiply both of these by 2, you'd also have 2x approaches 0 because 0 times 2 is still 0. So I could rewrite this limit as the limit, 1/2 the limit as 2x approaches 0 of 2x over the sine of 2x. And now this is really looking familiar. I could do a u substitution, let u equal 2x. And then I could simply rewrite this as 1/2 of the limit as, notice, u approaches 0 of u over the sine of u. And that exactly matches what we said over here. Doesn't matter what variable I use. X approaches 0 of x sine of x over the sine of x. Doesn't matter at all. The answer is still 1. And so this piece right here is 1. And so we end up with a limit of 1/2 times 1, or 1/2. Okay. And so when you get a simple problem like this, you'll notice in this case, the 2 is in the denominator. So boom, you get 1/2. You'll notice in this case, the 2 is in the numerator. And so you end up with just a 2. Okay. So this is the type you'll get to the point where you simply recognize those. Okay, number 6, this is from the movie Mean Girls. And you guys, there's always a combination of, the screenwriter, the people who write the script, talking to someone who's a mathematician and picking problems. I'll be honest, I'm not able to do this problem mentally at all. One thing I noticed is the denominator here says 1 minus cosine squared x. You could rewrite that as sine squared x. That's a trig identity. Then you have a sine squared here. You might be able to write it as 2 separate fractions or something like that. But to be completely honest with you, I can't think of a way of evaluating this other than using a tabular or graphical methods, which the character in the movie does not do. She simply thinks and she recalls back to this lecture where this boy's face comes to mind and everything else. And suddenly she remembers that the limit does not exist. Well, you can't just write that down and say that I know this from the movie Mean Girls. So what do? So in this case, I would recommend actually typing it into the calculator. And that takes a bit of work on this particular function. So I'm going to enter the numerator in parentheses, the natural log of the quantity 1 minus x. Okay, I got that. And then minus the sine of x, and close the sine of x, and then close the numerator. and then divide that by, okay, in the denominator, I have 1 minus the cosine of x. Now, what's funny is the notation is different on a calculator than it is on the paper. You write, you can square that, and the calculator is not squaring x and then evaluating the cosine. It's actually evaluating the cosine first and then squaring it. And so there we have it. Okay, and then the next thing I do is change this to an ask. And then when I go into the table, I'm going to enter values. Let me delete these values here so that I can start fresh. Remember, I recorded this video earlier today at school and it failed. So, all right, what I'm going to do is plug in numbers very close to 0. So if I plug in x is 0.1, oh, make sure you're in radians mode. Hit mode. And there we are in radians mode, so I know I'm safe there. So let's go back to the table. If I enter numbers close to 0, like 0.1, this is at negative 20.59. 0.01, negative 200. 0.001, I have negative 2001. 0.0001. You guys can see this thing is going to basically negative infinity, okay, as I do this. So I end up with, as x approaches 0, the limit as x approaches 0 of, I'll call this the function f of x to save time writing. This one approaches, okay, I'm approaching from the right. I've been putting in positive values. So 0 from the right approaches negative infinity, okay? And then what happens if I type in numbers close to 0 on the other side? Negative 0.1. Well, now I have a positive, basically 20, negative 0.01. Now I have positive 200, and now negative 0.001. Now I basically have positive 2000. Okay, and so what happens here is the limit as x approaches 0 from the left of this function f of x, that limit approaches positive infinity. Okay, and since these two do not match, one goes up to positive infinity, one goes down to negative infinity. This limit does not exist. And fortunately, in the movie, the character, I forget her name in the movie, but the character states the limit does not exist, and she wins the mathletes competition or whatever it is. Okay, so this one doesn't exist, and I found that out by just punching things in a calculator here. Okay. Alrighty, next one, number 7, the squeeze or sandwich theorem. The idea here is that as x goes to 0, this term here just starts oscillating crazily. You know, 1 divided by 0.01, you know, you're taking a sign of something that it's just going to keep oscillating. But the thing is, this portion of this function, the maximum it's ever going to be is a positive 1, and the minimum this term is ever going to be is going to be a negative 1. And so what we do is we sandwich this limit, the limit as x approaches 0 of x squared times the sine of 1 over x. We sandwich it in between the upper limit, where we decide the limit as x approaches 0 of x squared times positive 1. And in the lower side, we sandwich it, the other piece of bread is limit as x approaches 0 of x squared times negative 1. Because this term here is always going to oscillate between positive 1 and negative 1. It can't escape beyond that with real numbers. So what's nice is in this case, it's times a positive 1. This is times a negative 1. What's nice about this is I can evaluate this limit by simple substitution. Just put a 0 in there. 0 squared is 0. And this one I can evaluate by simple substitution. Put a 0 in there, and indeed you end up with another 0. And so what the squeeze theorem says is if you have a function that's always greater than the function you're trying to evaluate, and that one has the same limit as something that's always lower than the function you're trying to evaluate, that if those two limits match, then this has no choice. It gets squeezed in between. It gets sandwiched in between the two limits, and it would also have to be 0. And so the answer is 0, and that's by the squeeze theorem or sandwich theorem. Okay, and then number 8, you guys, I don't know how much time you spent with this. Apparently, you guys learned this online in March, April, or May. What L'Hopital's rule says is if you directly evaluate an expression like this, if I replace x with e, I have e to the e minus e to the e over e to the e minus e to the e, and that equals 0, and that approaches 0. And so I end up with this indeterminate form, 0 over 0. And so what L'Hopital's rule says, make sure you cite that you're using this at each step. What L'Hopital's rule says is when you have an indeterminate form of 0, 0, you can reevaluate this limit. Same limit, x approaches e, but instead of this function, you take the derivative of this function with respect to x, whatever that is, and you take the limit of the denominator function, and you can evaluate that using the derivatives. How fast are these limits changing as x approaches e? How fast are these two functions approaching e? The derivative of these two functions approaching e. The ratio of those rates of change will tell you what that limit is, which is kind of cool. So let's do this. The derivative of e to the x is e to the x, and e to the e is a constant. Even though I know you'd have to punch it on a calculator, it's still a constant. And so that's minus 0, or just e to the x. So I'll put that in the numerator here. Okay, and then for the denominator, x to the e, that's the power rule. That would be e times x to the e minus 1. And again, e to the e is constant, and so that would be minus 0. And you'd end up with e times x to the e minus 1. And so I'll put that up here, e times x to the e minus 1. And what L'Hopital's rule says is if that limit exists, then that will equal the original limit here. Okay, and so now the question is, can I just use substitution, which is the most powerful method that we have? Well, if I put an e in place of x, I get e to the e, which is a finite number. And then here, if I put an e here, I'm not going to end up with a 0 in the denominator. So I'm perfectly justified to simply substitute away. So I'd have e to the e over e times e to the e minus 1. And that looks a bit messy. If you have the multiple choice section of the test, they probably won't offer that as an option. Notice that e by itself is just e to the 1. And the rules of exponents would say you add the exponents. If you have the same base, you add the exponents. So you'd have 1 plus e minus 1. But think about that, e to the 1 plus e minus 1. Well, wait a minute, the ones cancel, and you end up with e to the e over e to the e, e to the e over e to the e, which is just 1. And so this limit, that complicated looking thing there, is simply equal to 1. Okay, so you guys, that is not everything you're going to have to know about limits, but it summarizes 8 ways to evaluate limits. For homework, it's limits doku. I assume you're familiar with Sudoku. If you're not, that's fine. Complete the worksheet. It basically gives you a bunch of clues, and as you evaluate each limit, it tells you what number to put in each square of the Sudoku chart. And you don't have to finish the Sudoku. That's just for fun. I love the challenge of Sudoku. I love to work those problems out. So once I get the numbers in the grid from the limit, then I can't help myself. I actually want to work the whole thing out. Okay? All righty, guys. That was a pleasure. Take care of you guys. Be well. Stay out of trouble. Okay? Bye-bye.